So as the slides are getting loaded, I'll just quickly introduce Professor Ram. Professor Ram obtained his BS degree from the University of Madras in 1981, BE degree from Indian Institute of Science, Bangalore in 1984, and the PhD degree from TIFR 1992. He has been engaged in research in speech processing and related areas for close to 3 decades. Prior to the present position, he was professor at PES South Campus between 2013 to 2017. He has worked in various institutions and universities such as TIFR Bombay as research scholar, fellow and reader, University of Valencia, Spain as visiting scientist between 91 to 92, ATR Advanced Telecommunications Research Laboratories, Kyoto, Japan as invited researcher 96 to 97, IIIT-Bangalore as research associate 2000 to 2004, and Siemens Corporate Research and Technology between 2005 to 13 as senior member technical staff and as head of the speech research group, also called Professional Speech Processing India 2006 to 9. He has over 65 research publications in these areas in peer-reviewed international journals and conferences. He is also the author of a Springer monologue on ultra-low bitrate speech coding, Springer, New York, 2015. Apart from this, he's also a very liked professor here at IIIT-B. He's very famous, his lectures, and I've also attended some of his lectures. So the good thing about it is he will take you from 0 to 100, right? Not from 0 to 50 or 50 to 100, but he'll take you from 0 to 100. So it's very nice of him, yes. And he also mentors a lot of projects and students here. He's also mentoring me and Neelam and Vinod, other faculty here at IIIT-B. He's also a well-respected speech researcher in terms of workshops and talks that he gives in the speech community. He's quite respected. Just a small anecdote, one of my former roommate, classmate, whatever you want to tell, Sriram Ganapati from IISc. So I was trying to establish collaboration with him, right? So he was saying, yeah, we can do it, but if you can pull Professor Ram, then it is sort of certain, right? That's what he said. So he's sort of very well respected. And given his so many years of experience, it's only, we just have to sit and listen about the topic, which is some paradigms in ASR. Okay, over to you, Professor Ram.
Good afternoon. Firstly, thanks to Dinesh for the warm introduction. In a way, I am kind of, I owe it to him for being here because he and Neelam had asked me when I was interested whether I want to come over in some sense and start a more serious activity in machine learning, not only in speech, but the kind of things they do, vision, image processing, video analytics, biomedical imaging, NLP kind of things. So it worked out. I'm kind of thankful in that sense. And I've been associated with IIIT for almost 10, 12 years, right from the time when I was in Siemens. Professor Sadagopan had kindly kind of made me part of the faculty selection committee. So I know quite a few of young faculty. I used to sit on the committee panels. So I know the way the clock ticks in IIIT for so long. And I'm hoping I'm fitting into the groove. So the jury is out with you. So now I'm going to talk about some paradigms in ASR. Of course, there were few options of what should be the way I should present this. One format was to ask my students who are masters and PhD students to also talk about their part of the work. But given that they're almost in the starting stages, I thought it's probably undue burden to let them face the audience with a confidence that usually comes when the results are ready after 1 year, when they're ready to write. The work speaks for itself. So I thought I'll wait for one more cycle. And the second kind of deliberation was whether I should talk about a particular topic, which is more contemporary and which gives a sense of where ASR is. But instead, I choose to talk about what work is going on among the students. That way, it also exposes you to what the MS PhD students are embarking on now. At the same time, kind of covering ground on why we chose those topics, the reasons being that this is the contemporary and open problems kind of thing. So that way it gelled in well. So I'm going to talk about, it's a little ambitious. I put here 8 topics being followed by 8 of my students, starting from Manjunath, He's a part-time PhD, and I think I forgot to invite him. I didn't send an email. He's in ISRO, and he's very busy with his own promotion interview this month, and he apologizes that he can't visit institute very often. And he was a full-time student here with Dinesh, and then he went to ISRO, and then he also converted to become a student with me. He works on multilingual approaches, specifically Indian languages, and he focuses a lot on what is called articulatory parameters. And I'll spend quite a bit of time on this articulatory approach, and that is his mainstay. And the second work is by Vikram, who joined last year. He has a long association with the faculty in IISc. His topic is mostly on co-articulation modeling for ASR, and it's a very fundamental research problem, and we'll see what that is. And he's also part-time PhD. Vandana is a professor from PSIT. She registered with me long back, 2 years back. She's a faculty here, converted from Neelam to me. She works on a neural network formulation called associative memory networks, essentially adapting associative memory networks for speech recognition, specifically continuous speech recognition, something which hasn't been done at all. I'm not putting a parity between these topics, but Vandana's work, if it hits off, it will be a major breakthrough. It will be a very major breakthrough. So we are seeing where it stands. And Shrikanta, who is here, he is going to work on a very contemporary approach, which is just 2 years old in the community, which is called end-to-end approaches and attention-based model. Some of you work on image and video analytics with Dinesh and Neelam would know that attention-based models are becoming a in thing now. What is published is just about a year old, and he's going to focus on that. Srinivasa Raghavan is almost kind of contemplating to look into a topic called zero speech. It has again a lot of fundamental underpinnings about how humans do speech, how a child learns speech kind of thing. So zero speech touches upon such fundamental aspects, even though it also has not a commercial spin, but I would say a technology spin in terms of asking how machines can mimic humans in the way that child picks up a language without knowledge about script or phonemes or anything else. How does it do that? So that's the thing. And I have put here also a small variant, which is the Samsung Masters and PE thesis, who are working with me till next June on something called acoustic subboard based end-to-end ASR. This is something which has evolved during the Bell Lab time, about 20 years back, and it has gone into the background. And there are few people who are still kind of advocates of this kind of approach. And at least I am a great fan of this approach for its many appealing aspects. And we are trying to rejuvenate this notion within the concepts of end-to-end and attention-based and zero-speech models. The Samsung group of 4 people are really working on this, and some of the work would probably go into Shrikant's and Srinivasa Raghavan's work. And finally, I'm also putting a small variant of this MS PhD work, is the MTech work by Chella, Priyadeshini, and Anup. They are not here. They worked on a classical machine learning problem applied to speech called semi-supervised learning and active learning scenarios. They did a phenomenal amount of work in just 3 months' time. Like they started with the PE and then they had a 4-semester MTech work. So it was published in the last InterSpeech, a flagship premier conference of speech. And it's one of the very seminal work we have really contributed. Many groups like Amazon R&D and Google, they came to our paper session and they're very keen to look at this because this is exactly the kind of topic they are very, very interested in, right? So I'm not sure whether I'll really cover all of them. If I want to do justice to all of them, I have to do certain amount of breadth first, as well as let's see what kind of depth first I can do justice to. But ideally, I should really do all of them. So no particular order. I want to follow this sequence because they dovetail easily and builds up the concept fairly with a good flow. So first I'll talk about the ASR problem space. Where are we? What kind of problem is it? In fact, as Professor Asi said, MINRO project, which is now kind of active across the institute, apparently one of the reviewers who saw my proposal, which is of course a joint proposal with my students on Indian language, ASR for Indian languages, in a multilingual scenario, including machine translation and across Indian languages, as well as spoken dialogue information retrieval system. And apparently he said, oh, this is nothing impressive. I mean, we have seen this. If I open a TV and switch on a channel, I see a Telugu movie, I can switch from Telugu to Hindi to Malayalam. I can listen to the movie in any of the languages. So why are you still talking about machine translation in Indian languages? So apparently he had to defend me saying, no, it's only the dubbed version, manually dubbed version. And Tata Sky allows you to switch between any one of them. They're all canned data. There's no online machine translation, which is so good. So thanks to him for coming to my defense. But at the same time, in the next 10 slides, I'm going to tell you practically about the fact that most speech researchers, right from the time when we started working in speech research 40, 50 years back, have been on the defensive anyway, for various reasons. I mean, it's no surprise that a poorly informed reviewer puts you on a back footing, but it has been so for quite some time, regardless of where technology is, and more so now, mainly because ASR has probably arrived, because last 5 years before you wouldn't have seen any product space. So we were all happy when I was in Siemens or before in TAFR saying speech is unsolved problem and we have enough time to go on. Another 50 years we can do research. We'll still do research, but not the kind we thought before, because much of the last 5 years of research has culminated in product spaces. So you do have in your own room or in your mobile Google Voice Search, Cortana, Siri, Nuance Dragon, and Skype can do translation, Amazon Alexa kind of thing. In fact, my son has Google Alexa. Google gifted me a Google, not Alexa, Google Home. And he happily uses it, much to my chagrin, because I keep telling me I'm doing research on unsolved problems, and he's happily using it every day. It works very well. But so in fact, he asked me, what is it you're doing? Google has solved everything. So the point is, it's almost like, it's still not so. It's almost like asking if you have an aerospace department in IIT or IIC or MIT or Stanford, are they obsolete? They still teach aerodynamic courses, and they still do research in aerodynamics, even though you have pretty much good airlines flying all over the place, regardless of mishaps once in a while. And finally, coming to the nature of what we are trying to do, like aircraft building, we are in the business of automating something which is unique to humans. Typically, we are talking about speech and language, which is a unique faculty in humans. It has evolved over evolutionary time scales. It's not like playing chess or even doing medical diagnosis, because that kind of knowledge can be acquired in few years' time, and you can become an expert. And there are equivalent expert systems and engines which can beat Kasparov or pick up medical diagnosis like what Watson does. It pulls over oncology database and says it can aid the physician to help him out with the treatment therapy, right? So the point is, these are all short time scale knowledge acquisitions when compared to speech and language, which is ingrained into a species on evolutionary time scale, and we still haven't uncovered the so-called speech code which ticks inside, like the gene code. We still haven't uncovered the cognitive basis of why we are able to do speech and language. So what you see as the last slide's product spaces are engineering approximations. Like I always say, engineering approximations like aircrafts don't have wings. They don't flap the wings, but they are very good mathematical and engineering approximations of birds that fly with something very good. They do something very well when compared to the biological counterpart in some dimensions. Some dimensions they excel, right? So those are all various adjectives like more, better, faster, cheaper kind of things. We are so used to this, we don't think that engineering approximations are outdoing what nature could do. At the same time, many of the engineering approximations are not supported by fundamental understanding of the biological counterpart. So these two worlds live happily aside. Very similar thing is going to happen in speech and language. There are going to be products in the next 5, 10 years which are going to be as good as human, but without probably a community of people who claims that they have a deep understanding of the biological system or the human cognitive process. So to that extent, those kind of areas will continue to be of immense interest, just as aerospace engineer will be having a holy grail of having a effortless Iron Man kind of thing, flapping the wing and flying. So this goes back to the days of Daedalus. Daedalus is a person who wanted to escape a prison. He put on wings made of wax, and he and his son Icarus flew, and they were successful. But they got carried away, literally carried away. They went so close to the sun, the wax melted, and they fell to their death. So the point is, it's definitely holy grail to create biological realism. So whatever I'm going to talk about, or whatever is happening in the community now, the engineering stuff is all devoid of biological realism. So there's definitely going to be a major direction of people wanting to catch up with the so-called biological realism, which is quite a far way. So, lot of things, yes. Right. I would say right now, if you look at it, the priority of things you would like to solve, we don't even have the clue about the biological counterpart of what you are trying to do. For instance, at best we'll have information about feedforward networks or recurrent networks. And none of these have a biological equivalent. Even though the Hinton kind of people published somewhere saying, I know there's an old neuroscience paper which seems to mimic feedforward or backpropagation. Clearly there isn't. So I would say we still have to come to the few layers, not the deep layers, few aspects of the biological realism. So I'll be happy to get it right, even at a cost of very poor energy efficiency, and solve the energy efficiency as the last problem. I mean, it's one of the last problems, I would say. That's the least of the problem to begin with, because I'm happy with a very poorly scaled biological system if I can hit upon the principle, right? So right now, the claim we are making is such things haven't come into speech or vision or NLP, right? So we are still going by at least two things. When I say engineering approximation, nothing to scoff at. They are still supported by math, because the aircraft flies because the aerodynamic math is so good, right? So to that extent, many things which are not having the biological realism are still having the counterpart of math, which is good, because as Russell said, why is mathematics so effective? You do scribble something in paper and seems to capture what nature does. So to that extent, there is a biological realism in some form sitting inside the math equation, right? So we have to acknowledge that, and that still goes on. So that's some kind of reassurance to us that we are in the business of trying to establish human-machine communication, right, which is essentially in the spirit of automation, like what happened in spinning jenny and various other industrial renaissance kind of things, right? So coming to just a few slides of 2 minutes of something nice about speech and language. This, of course, post facto, not that I got into research because I knew these principles. Nice thing about speech and research is, speech and language is, when people now ask about AI could be anything. Could be chess playing, could be oncology diagnosis, could be Watson winning Jeopardy, could be a driverless auto system, could be anything, could be missile guidance. You can talk about anything under AI, which basically tries to, in a nutshell, do what humans do, what humans are good at, right? Trying to make machines do what humans are good at. And as I told you, there's always a debate about whether the deep blue is intelligent. And naturally, Turing was one of the person who coined the definition of what is intelligent, what is machine intelligence. When will you consider a machine to be intelligent? He said, put an entity in a room. It could be a man or a machine, and you ask somebody to interact with that entity without knowing what it is. Let him spend any length of time on any kind of topic. At the end of it, and he says, I can't distinguish what is inside. Then that machine, if it were a machine, it would have passed the Turing test. So right now, it's still a holy grail. Nobody has come close to it. There are contests of people trying to build Turing machines, which try to have a code, a software sitting here, interact with the human, typically on a text basis, which is you have a keypad. But it's just addition to add a speech dialogue, speech modality to it. Then it looks like you talking to the machine, like the Space Odyssey HAL computer, where the astronauts could talk to the HAL computer. And so the point is, the Turing intelligence test seems to tell you that the very essence of intelligence seems to be embodied in a machine having as much intelligence as a human to be able to carry out such conversation. For some reason or other, the conversational aspect of building an engine here, what I've said, seems to define the very basis of intelligence, which is nice because I don't have to go searching for what is the toughest AI problem. I would say speech and language, at least by Turing definition, is definitely the toughest AI problem, because once you crack it, you can build a machine which is truly intelligent according to Turing test. And believe me, it's still tough. So I think Turing was right to a large extent, right? So essentially, if you look at the typical engineering approximation of a conversation interface, we are talking about probably a text mode of interaction, or a speech converted to text by ASR in one direction, TTS in one direction, and you can pretty much say, how do you do this? A lot of stuff going on, engineering approximation, math, of a lot of NLP going on here. But right now in my talk, today's talk, or my own research, I stop here. In fact, most of my research is on ASR related topic. And ASR can be very simply defined as going from speech to text. So it looks like a very glamour stripped version of the whole business I talked about Turing machine. But that itself is quite a challenging stuff, right? So that is essentially the anatomy of a dialogue system. It has many components, including a speech recognition, going to the words, having all kind of back-end dialogue management, NLP stuff, language generation, synthesis so that the human can interact with the system, maybe do information retrieval from a database, some of the things like you routinely do with Siri or Cortana or Alexa. So the focus here is this. This itself is a considerably challenging problem. It has occupied people for ages. The question is, this happens to be the weak link in the entire stuff. Because if you don't have this, the whole thing falls apart. So people have been waiting for the ASR to get better, and that's why the Google and the Siri, they're all available now, thanks to the fact that deep learning and machine learning has helped to push the ASR performance to a point where these kind of systems are meaningful. There's robustness inbuilt into the ASR system that the other things will hold, right? That's what is really happening, right? So I'll quickly give a schematic of what I said just now. You have the complete automatic speech understanding and dialogue is all of these things. Your front-end ASR followed by the NLP dialogue components. The ASR itself, classically, conventional systems look like this. There's always a feature extraction. All of you know in image processing, you'll have to extract features, which makes sense, right? Which represent the particular object, image or sound, faithfully in the higher dimension space. In the higher dimension space, what you get for speech is very unique because you get a feature vector sequence. And you have to reckon with the time as the important axis. And without the time, if you do anything, nothing makes sense. So it's a very unique problem, something unique to speech because you are dealing with not a single feature vector, but a feature vector sequence. On this, you have to do a hypothesis testing to find out what words might have been spoken. So you have to match the decoding to what might have been spoken. And what comes to your help are things called acoustic model, which is essentially goes into statistical machine learning. And before the word machine learning came into picture, we used to just call it statistical PR, pattern recognition. And the idea is to model the PDF of each sound class in the feature space by any number of any type of probability distribution functions. That's about it, right? But that itself was so tough. Even now it's so tough. And the very notion of deep learning, like deep neural networks, where are they playing a role? Here. They are playing a role here. So between the last 5 years, between 5 years before and now, if you ask where did the advancement come from, the breakthrough come from, here. It's here. The deep learning is essentially a statistical machine learning theory, which is helping you to do something better here. None of the other things need to change dramatically. So even now, if you look at when I teach a ASR course, I always say much of what Google Voice Search would do would be pretty much the good old stuff. There's no major difference. But in the last 2 years, even this structure has changed. People have started dropping all of these things. Your so-called end-to-end approaches completely drop all of these things and directly take you from the signal to the decoding. The decoding could be a letter sequence, like what you see in a Google Voice Search. Because once you get the letter sequence, you can paste it on the search bar, and you get your action. Or it could be a word sequence and so on. Or it could be some action based on some understanding. So end-to-end systems do come away from this structure. And my own take on this, as with many other people, I want to put a quote from the Daniel Povey, who is the kind of pioneer behind a toolkit called Kaldi, which some of my students use routinely. He's in JHU, and he was a PhD from Cambridge University. What he said is, hey, end-to-end, I'm very skeptical. Because what you have done is we gave, 40 years back, we gave a structure for the machines to obey. The structure is meant to facilitate breaking down the problem in such a way that different things about speech are handled differently. But you take all of these things and make it end-to-end, I'm very skeptical. Because what you're doing firstly is to make the signal look unstructured, which will have its own debate on why it's advantageous. But that point is you're increasing the variability. All the structure came in because you wanted to reduce the variability. So regardless of who spoke, show me the map of electronic city, whether you are a Korean guy or a Finnish guy, there's a lot of variability in the speech which you will not notice because when I listen to it, I don't care who spoke, I'm getting the word sequence correct. But the machine is confronted with large amount of variability, which is what these statistical models have to cope with. So the take now for many people is they're not great fans of end-to-end because you unnecessarily increase the variability which the machine has to cope with. So there should be something to be done to bring the structure back. They're not throwing the end-to-end out. They're saying it's good. There's a lot of data-driven nicety about the end-to-end, but put the structure back. So that is really one of the major driver for me because I'm an old school person who has seen many hype cycles, not only deep learning, not even machine learning, HMMs, before that expert systems. I've seen enough cycles go up and go down. So I know how people position themselves either in research or industry. And for instance, IBM itself has been in and out of speech for 3-4 decades. There were teams which grew up to the peak, they delivered some system, then it just completely, the whole team went away. Where did they go? They went to hedge fund management because they found time series is similar to speech, so they made a lot of money out of doing HMM stuff on the time series. Right. 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 I see. When they go to time series analysis, when they go to stock market prediction. So these kind of cycles have gone in and out. And the point is, repeatedly, there have been two communities of people, which is what I gave in the abstract of my talk. Two communities. One community is the good old acoustic phoneticians who know a lot about speech in terms of their production knowledge, perception knowledge. And they say, hey, these data-driven systems don't respect any of that knowledge. They do pretty much starting from a feature vector sequence, I'll get a letter sequence. And it's all conditional probability. They don't like it. They say, where's the speech knowledge? The machines are completely devoid of speech knowledge. And these guys say, hey, it's fine, because I mean, I'm working with a very well-defined something like a sequence-to-sequence translation problem or a very specific statistical machine learning problem. Why are you complaining? The other guys say, hey, no, if you were to put in this kind of knowledge, it's going to help you. It's going to help you more cleverer machines. So this debate has been there through all these 3-4 cycles I've seen. The debate is still live now. It's more relevant now. And some of my students, I kind of egg them on to look at that amalgamation of not only just pure data driven, which you can crunch in a GPU server for 1 week and get some results, but to see where meaningfully you can bring in the knowledge. By knowledge, it has many shades. It's not just acoustic phonetic knowledge. It could be the topology of the HMM. It could be the architecture details. It could be how you initialize the architecture. Could be many things. I'm just saying 4. There could be 50 things sitting there about how to integrate that knowledge and how does it get integrated, right? So that's essentially the mainstay of my work, probably in the next few years, my students, and some of the things I'm going to talk about. So,
the virtual system today is still very poor handling of other aspects.
Exactly. Yeah, precisely. In fact, precisely. If I told you about 50 things which will be sitting there. I told you about 4. The 5th one, the very central one, is if I look at a Google voice search, it has to work across the globe. So it could be a Korean person speaking English, or a Japanese speaking English, or a Malayali speaking English. They all have the effect of what is called L1 or L2. L1 is the first language, L2 is that English they are talking to the engine, and the L2 carries all the signatures of L1, which makes it called accented speech. Right? Could be a French guy, could be a Finnish guy, Russian guy. And Google has very, very promisingly handled that to a large extent. And where does it get handled? It's not in the end-to-end system, but when you provide the so-called pronunciation model. So as I told you in the block diagram here, this lexicon carries that information about how the different words are pronounced by different people with different accents. So that is also a stochastic model. You can have stochastic pronunciation model that has to absorb this information about how the words look like across the population. Yeah. That goes into NLP. I'm not doing NLP. I'm working with ASR, which is just signal to symbol. So I don't know if Raghavan is here. He will answer you on the NLP side, because that goes into the syntax and semantics of text sequences. I'm not touching this, right? So they do pretty well. In fact, multilingual systems, they do very well. In fact, if you ask a question about the lexicon, so if I may have a vocabulary of 10,000 words for a particular language, but I'm coming to that. Yeah, they have a special name. They are called morphological variations of the word. So there are algorithms which will derive all morphological variations of every word, which you will see in the actual language. So, right? So if you take a particularly Indian language, Indian languages are notorious for the morphology, right? You may have a root word, but the root word gets morphed into so many morphological variations, and we call it sandhi and the word joining kind of thing. But there are algorithms which can expand the lexicon to include the morphological variation so that you can handle continuous speech. It's almost a done thing. It's no big brainer, right? Okay. Yeah. Yeah. Sorry.
The learning which happens, particularly if you use the eyes-on stuff.
Right.
You find that after 10 days.
Right. So this is called the same thing what Chella worked on, semi-supervised and active learning. The learning takes place in any one of the blocks. It could happen in any one of the blocks. For instance, if it happens in feature extraction, essentially you are learning about the environment, and you learn to subtract the noise out of the environment because you now have a clue about the spectra of the noise. A simple example. Or you could learn the lexicon because you think the family here uses a certain pronunciation of a certain kind. You can modify the pronunciation to create what are called pronunciation variants. It can do mostly, predominantly in the acoustic model, where it updates the acoustic model parameters, could be HMM or GMM or DNN parameters in such a way it tunes to the speaker rather than becoming speaker independent. When it ships out of the factory, the Amazon Alexa is stupid. It is speaker independent. It's trained on 10,000 hours of data, 1,000 speakers. It's no good for any one speaker. For it to become good for you, they have to do that extra speaker adaptation. IBM used to do that. When IBM Via Voice was there, you buy it for $30 from a shop, then you have to sit here in your bench, in your desk, and then read out a paragraph so that the machine's acoustic model trains to the particular speaker. Only then the performance becomes manageable. So these are all, tools of the trade which people have been using. And that's why you notice a visible difference after 10 days. Yeah. It's done for? Accent also, exactly. It is done, but the question is where you incorporate that new knowledge which is coming online. These are called online rapid adaptation because you are rapidly adapting something about the system. What is that something? Could be the features I told you, what kind of features you are extracting, could be the lexicon, which is the pronunciation model, could be the acoustic model. Mostly the onus is on the acoustic model because that is what is capturing the statistical variability of the sounds you speak. So the accent carries more there, right? What carries more into pronunciation is called dialect. Dialectal variation, could be accent variation. So these are also intertwined. You can't even separate them out. You don't even know what effect influences what. This is still unknown. That's where the speech code people, the guys who are speech knowledge guys who say, hey, we know that. Why are you not taking that knowledge? That's one of the example I'm talking about. Right. Very good question. They could be completely data driven, or that is the system could be agnostic of what it picks up, but you have to provide a framework of what it's picking up. If you say I'm going to affect certain filter banks, you have to say which filter banks. That meta level knowledge doesn't come by itself. That's exactly where the biological realism plays a role. You do not need any meta level. Tomorrow you can get used to the Russian accent after 3 days without you telling yourself where you should focus. These systems still need the meta level framework to know where to adapt, what to adapt. Oh, they do well. In fact, particularly Google, any of the Amazon Alexa, they do well on Indian languages. What is shipped in the factory works across the country reasonably well. But accent, the way you handle accent, is that the most efficient way to do it? Or is it going to be robust for next 1 year? Or is it going to be something called session variability? It works for me today. After 1 month, my voice changes. Is it going to work? These are still important questions we are asking. Oh, it's an ongoing thing. These algorithms are adapting on an online manner. And it's online with every utterance. With every utterance. So I'll I still have a long way to go. It's 11th slide, 1/10 of the slides I have. So essentially I'm speaking, I think I have to do less justice to some of the students. I'll do that. So typically the ASR problems is something as unglamorous as this. You are given a speech signal, and you want to maybe represent it in the form of a time frequency, what is called spectrographic representation, which gives you how the spectrum is changing in time. This is a short-term spectrum. And then the ASR's job is just to say, hey, this speech waveform is nothing but the new bricks fell over, right? And what should be the output, which is the decoder output, should be matching with the ground truth, which means if you are to give the speech signal to a human, he says it's new bricks fell over, you expect the machine to also say the same thing. That's pretty much a very simple-minded problem. Very simple-minded definition, but it has engaged people made enough people's life difficult. Still continues to because I wouldn't be in the job otherwise. so some speech basics quickly in 5 minutes is you have a time domain signal, which is the speech signal I showed you. And typically in order to capture information that carries information about the identity of the sound. Suppose I say show me the map and you're asking about the phonemes sh, o, im, e kind of thing. And why does the sound change? Because my articulator is changing. So I know how to talk. By the time I'm 2 years old, the child talks all the sounds. It learns with mistakes. Initially, it makes all kinds of mistakes. But by continuous listening, it tries to match what it listens. And it perfects the articulation process so that all the sounds come out in such a way that it makes sense to another human. So by then, the human-human communication link is established. And the human decoder can understand what he's saying. And he can say what he's supposed to hear, what the other person is supposed to hear. So that kind of information is available in the short term of the signal. And what does the short term of the signal carry? It carries what is called the impulse response of the vocal tract. If you model this as a linear time invariant system, some of you who have done signals and systems, they will know that you are now dealing with entire speech process as if it's a convolution between something called the glottal flow with a linear time invariant system. That convolution produces speech, and from the speech you want to do a blind deconvolution, which has many names, but one of the things is called blind deconvolution, to be able to go back to the vocal tract characteristic, which in the signal spectrum, from the signal, if you take a short-term Fourier magnitude spectrum, it is sitting there. That information about the vocal tract is sitting there in the short-term envelope. That envelope is this envelope. So this kind of envelope says that the sound is R. If the envelope changes, it becomes E and Sh and In and so on. So typically the machine has to be provided with such short-term spectral information. This is a spectral information in grayscale moving in time, which is called a spectrogram. So you have to provide this information, and almost all machines now ubiquitously has to work with something of this kind, except the end-to-end systems. End-to-end systems are arrogant. They say, hey, you don't tell me what I should look for. I may look for anything. Why are you telling me I should look for spectra? No matter that your vocal tract is has a transfer function, and the transfer function can be modeled by a spectrum. No matter that your inner ear has a cochlea, which has a basilar membrane, the basilar membrane is doing a spectral analysis, like a Fourier transform. These guys say, I don't care. I let the math decide. So what's happening? Like with any other engineering stuff, the math takes over and probably does as well as a neural biological realism, which is very good. Now there are a lot of people working on the fact that math of certain neural networks can pretty much do very much what you're doing without being told so. That's something remarkable. And the end-to-end systems are the only guys who say, I don't need any of this bag of tricks. I can start with a speech signal. I will pick up what I want. That comes under the area called representation learning. So the whole area called representation learning, which says, regardless of whether it's an image or biomedical signal or speech or audio music, I will build networks which have the right math to pick up the right information which I want to discriminate between the classes. So if my problem is to discriminate between one kind of sound, sh, with the other kind of sound, e, I know how to do it because my representation learning layers are optimized with a loss function to discriminate the sounds. And they're very good. So if you go back and look at the representation layer, it turns out they learn pretty much what you started with. So then you can say, tell the guy, hey, you never had any chance. I was right all the time. This guy will say, hey, look, I didn't need your knowledge. I'm pretty much good with my math. That's really what is going on. They're not fighting, but they're happy together. And so essentially, what you do is you do a lot of math, signal processing, and for each short-term window, you come up with a vector. This vector is representative of the short-term envelope in the time frame. And what has happened now is you've done what is called parameterization or feature extraction. The short windows of speech has become a vector. And how does the vector look like to a machine? It looks like a point in a d-dimensional space. So if this is a d-dimensional space, where d is the dimension of this vector, your speech for 1 hour is nothing but lots of points in the d-dimensional space. And what kind of structure does it have? It has clusters, clusters corresponding to the different sounds, like the sound A and the E and the O and the IR and the Yesh. And they're all well separated, hopefully, but usually they're not. Because if you look at the blue patches are all clusters of one speaker. You put one more clusters of another speaker, they start overlapping. They're different because the speaker's anatomy is different, so they are different. But if you take 100,000 speakers, like Google's database of 50,000 hours, you'll get a big cloud, which is called a multimodal distribution. Now, the acoustic model, what I told you is the key. I always say, if you're not convinced why it is the key to ASR, only thing you should know is Google has a full department called acoustic modeling department. And there are n number of people working on only acoustic modeling. So it's so very tough to do. So what you have is a multimodal distribution which can model by a GMM, a mixture of Gaussian. The nice thing is it doesn't work. You need something more clever, mainly because what you see as a sound is not a bag of vectors. It has temporal dynamics. So your speech makes sense because you're listening to it in sequence, right? So when I say more, I'm actually going through a trajectory which looks like this. And to make it more specific, if I say Sony, I have a feature vector sequence which looks like a beads on a string. And the machine sees that. And it has to start modeling statistically variable versions of this. If I say Sony 1,000 times, spoken by 100,000 people, I'm going to get the bundle of vectors, and I need to model this. No longer a cloud of vectors, but a bundle of vectors. Who does it? HMMs. So until 10 years back, everybody was happy with HMMs. So HMM is basically Liddell-Markov model, and they were pretty much doing the job, right? And I'll go to that slide directly. And HMMs are basically looking at the R sound. As I told you, the R sound is very complex. It is a mixture of many people's R sound. It looks like a very monstrous space in the feature space. It's not well behaved. The R sound could look like that. The E sound could look like this. They are interlocked in such a way. In pattern recognition, machine learning, you call it as linearly non-separable classes, or hopefully, if they are separable by nonlinear surfaces. At least the hope is there's a nonlinear surface which will separate them, which is also not correct because they're not separable at all. That's what makes life difficult. That's why your Amazon Alexa will make mistakes. It will mistake one phoneme as another phoneme, right? So now the HMM people were modeling a single sound by multi-state system. Each state has a PDF, and what you're looking at is the bundle, what I told you, of a particular sound. Could be a word, could be a phoneme, could be a single sound. You are trying to model it as a sequence of states, each state associated with a PDF. That PDF could be the good old GMM. They used to be called GMM HMMs until 10 years back. People struggled with it. It was a plateau. Nothing changed. They were trying all kinds of things. There was a plateau. Then what happened? The deep learning came, and the GMM got knocked off by DNNs. So what really happened is everything remained same in the structure of the ASR system, but what you call as the density function associated with the state was replaced by deep neural networks. Then there was a massive breakthrough, and people never looked back, right? So I'll just go there directly. Right now you have a lot of deep learning variants. The domains are all these domains. The big players are all these guys. A lot of universities here who are a little defensive, but they will make fundamental contributions. They are waiting there just to do that. And again, a lot of variants like DNN, DBN, restricted Boltzmann machine, recurrent neural networks, long short-term memory, CNNs, and so on. Typically, depth essentially implies a neural structure of this kind. This is the depth. So you have more layers. They are called hidden layers. The hidden layers could be there in RNN, could be in LSTM, could be in CNN. They all follow that property that they are deep. Why did deep matter? I'm going to give a small visual insight about why deep mattered, and I'll come there. I told you about the plateau. The GMM-HMM system has been benchmarked extensively over the years, starting from 1980s all the way to 2011, and this is the plateau. A 10-year winter, nothing budged. There was a lot of progress on feature extraction, decoding algorithms, the pronunciation modeling, but the acoustic model didn't give way. It just said it held the performance nowhere. So for conversational speech, the kind of speech that we have routinely, the performance was 40% word error rate, which means one in every other word was wrong. You can do nothing with it. And people are still ambitious. It's like trying to build an aircraft while it is taking off. They were interested in building airlines, but the aircraft wasn't ready, right? And they were doing it. I was in Siemens. I was tortured for that. It's not nobody did that, but my business pressure said I had to build machines. They were nowhere when your performance was here, right? Then deep learning came, and what did it do? It pushed the performance from 40%. It pushed it all the way to sub 10%. Remarkable, right? And from here onwards, right? Many people take credit for that. I would say largely it should go to Geoffrey Hinton for the deep learning breakthrough from the theoretical side. And then people like Microsoft, Google, Apple adopted the theory. Now what happened here is now textbook knowledge. I teach an ASR course, right? Now from here onwards, there's no looking back. There have been several variants of deep learning, including RNN, LSTM, end-to-end attention-based model, and things are getting better, right? So that is a small story I want to tell you, and this I'll skip. There's a little more detail about why the deep learning systems are working. And to the extent that Microsoft published a IIIT transaction paper saying that how do you achieve human parity, right? On at least two databases, right? This was the IIIT transaction paper. They showed the correlation between machine word error rate and human word error rate and showed that you're pretty much on both sides, which was unthinkable before. So what was originally 6% human word error rate, they got 5.8%. So they were upbeat about it. It's a transaction paper, much noticed, but on two databases. This is not so far. What is now, they've coined a new word. When they started the research 40 years back, they said there's a speech database on which you do the benchmarking. It was called read speech, which means like a news reader, you read it. Then they said telephony speech, which means somebody talks on a telephone. And then they said found data. Found data means data could be from anywhere. Somebody talking on the phone from a bus, not controlled. Then now that these guys are closing in on the human speech recognition, they found the word wild speech. Wild speech, nothing is close to human parity. So that's still a game open. That's how things are going now, right? So let me look at the time. Good, 40 minutes, I'll cover almost all of the topics. Where did the gain come? It comes from Subproblems theorem, which almost nobody in the no practitioner knows very clearly. If you take a handful of Google engineers, ask why is your DNN doing well, they will not know it's because of Subproblems universal approximation theorem. It was found in '89. Until then, a lot of people have been working on so-called mathematical aspects of functional approximation. So what Subproblems showed is for feedforward networks, you can approximate the entire learning process as basically labeling input space. You have features, and the features have to be labeled. And what you said is, this is essentially a function mapping problem from the feature space to the label space. And you showed the fundamental theorem said, sigmoidal functions are universal approximations of any such function, arbitrary functions. The moment you can learn any such function, that means your feedforward architecture is able to map that kind of monster space, which is the region 1, into label R, and this monster space, which is the region 2, into the label E comfortably. GMOs were not able to do that. So that's why the DNNs started playing a role. And this was known to the early practitioners of the research. But now it has gone to the background. So people need to be reminded that there's a good amount of math working more than your Kaldi toolkit, which makes things work, right? So this theorem is this. I won't go into the details. All it says is, if I have a feature vector, all of you comfortable with the feature vector of some dimension m0, if f is the label you are giving to it, which is the monstrous R sound, every vector in that monster space has been given a label R, that f is that label, right? So if your floor is the feature space, every region is one kind of sound, and your label is one flat value. That is R for one region, E for another region. So you have discontinuous function, and we are saying feedforward networks can approximate any such function. That any such function is of this form, which is the sigmoidal approximation of a feedforward network with only one layer. So the Subproblems theorem said you can approximate any such function. You just give me one layer, one hidden layer, not less than one. What can be less than one? Good old what is called single layer perceptron. So Rosenblatt, 1960s, he started the perceptron, and he showed they have certain nice properties, but they stopped with being able to generate linear hyperplanes to separate two classes. So if the two classes happen to be linearly non-separable, perceptron didn't work. So you need an extra layer, which is what Subproblems pushed. He said, give me that extra layer, but with the caveat that it has to be astronomically large. The number of neurons in that hidden layer has to be very large, which is the number of neurons, M1. If M1 is very large, he says, I can map any function to, I can approximate any function, right? So that's a feedforward network with the central hidden layer. If M1 is very large, and he said in the theorem, I can find the constants M1, alpha, xi, wij, bi. There are parameters to be learned so that the approximation between capital F, which is what the system is doing, and what you gave it as a supervised label data can be minimized to any accuracy, less than epsilon. This was very fundamental, but by then people have started working with systems. They didn't wait for this. Empirically they found it's working, but he gave the much needed support, mathematical support. And what can these networks do? They can generate nonlinear separability between two such classes, which is your monsters R and the E and the ish and the ir in the phoneme space, right? So with that, next thing that happened is, since Subproblems himself in his paper said you need astronomical number of hidden layers, people started pushing in another direction. They said, why do I need very wide networks? I can have less wide networks, but deeper networks. Then the theorems came, particularly from Bengio and many other mathematicians said, what I would do with, I'll read it out. Some functions compactly represented with k layers may require exponential size with 2 layers. So if I were to be stingy with the number of depth, I work with 2, I need exponential number of neurons. He says if I can go from 2 to something k greater than 2, this width comes down. So what you are really doing is trading off depth to the width. So you don't need any more astronomical layers, and the depth can be manageable so that you can bring down the exponential complexity. That is fantastic because that's exactly what the deep learning community was doing. While all this was going on, people like Gunnar Fant, who is the original proponent of the acoustic tube of theory of speech production, classical speech scientist, he had this remark to make in one of the conferences about, I attended it, he gave a talk. He said, just read this out. 1970s, 80s is recommended. Meanwhile, the present statistical pattern matching, he was taking umbrage even to the old statistical pattern matching, which was working with 200 hours of data. Now it's 50,000 hours of data. I don't know what he would have said. He's passed away. He said, it's more straightforward and easy to handle, but in my opinion, it's not sufficient for reaching more advanced goals. This issue is illustrated in figure 3 by the picture of Mr. Speech Technology boldly surfing along without observing the knowledge barrier, which is the lack of the speech as a signal, what knowledge it has, where he might get stranded. And so this is the other school which is working. And really speaking, I still believe the real success will come from both schools working together. So that's now illustrated in this figure, which are presented in a keynote in the Interspeech conference in September by Hervé Boulard. Hervé Boulard is the director of IIIT, from where Dinesh comes from. Dinesh PhD is from IIIT. And he is a very well-known researcher. And he gave a keynote trying to balance these two. What is the traditional speech knowledge and where is the now current data-driven approaches? He said, hey, there was a time when HMM ruled the roost, but our gaining of understanding of speech science improved along with the performance. Then HMM GMMs really pushed the performance little, but we got a lot of understanding. That was the plateau. In the plateau, people understand a lot of things. Because they were pushing the plateau, they really got everything out of it. Then, I told you, the GMMs got knocked off by DNNs as the functional approximation thing, right? Then the performance improved steeply, but limited gain in understanding. It was just data-driven. Instead of GMM using 300 hours of data, Google said, I'll use 10,000 hours of data, because they have it, right? Then, the point is, the knowledge is so incremental. Now, with the big data trend, not only DNN, HMM, RNN, everything, LSTM, the understanding is going the other way, is asking post-218. Exactly, right. No, like what we say, we go to a pizza shop, there was a time when no hands was the key. So they'll say, I'll deliver you with no hands. Like no hands, it was made with machines. Now you have to pay extra for made with hands. So that's probably now post-2018 is the kind of people we, like old researchers who are still sympathetic and know about the other side of the coin, probably should make a difference, right? So that is really the first part of my talk, and still half an hour. I can spend 5 minutes on each of my students' work so that I wrap up by 3:30. Does it look all right? So in a way, I thought I struck the best of both views. One is the overall perspective, plus what we are trying to do, right? So first I'll talk about Manjunath's work. He's the oldest of the students I have. And this work, what I'm going to present is the paper he published in Interspeech. Again, very well received. There were scores of people at his session, essentially working on multilingual systems. The paper was called Multilingual Phone Recognition Framework with International Phonetic Alphabet-based common phone set and predicted articulatory features and feature fusion. It's very simple. What you are going to see here is the focus is on articulatory features. What are articulatory features? Essentially, I told you the linear time invariant approximation of the vocal tract allows you to estimate by deconvolution the vocal tract transfer function as a short-term envelope. If you don't know signal processing, don't worry about it. The point is, there's some math which allows you to go from signal back to the system. This is the system. This is also called a filter. The filter characteristics are essentially FIR filter. You can learn the FIR filter coefficients, and you're happy with it. But people say, hey, that's not enough. A deconvolution doesn't really do the job. You need a very detailed articulatory map of how your different articulators are moving. What are different articulators? Essentially, the lower jaw. The upper jaw doesn't move. It's stuck to the left skull. However hard you try, only your head will nod. But your lower jaw has to move to speak, right? And then the teeth and the lips and the tongue. Tongue plays a role. You cut off the tongue, that's why you know the old torture, they'll say if the guy talks too much, they'll cut the tongue. Even to children, they'll say, right, I'll cut your tongue if you talk too much. So the tongue plays a huge role in shaping the sounds, in shaping the vocal tract acoustic tube, which in turn affects the transfer function, which in turn affects the color of the sound, right? That's the way it goes. So people said, hey, if I go from the speech signal all the way back, not to your FIR filter coefficient, but go back to the articulatory, the entire system with the fine-grained map of the articulatory space, it's nice because regardless of who speaks around the world, a particular phoneme, the person has to move the articulators in a particular way. So what is this? It's a very important notion called in the presence of huge amount of variability in the speech signal, accented speech and so on, the articulator's representation gives a highly invariant representation of the signal, which the machine learning is happy. Why? Go back to the region. That monstrous R region becomes more compact. The variability is reduced in the articulatory speech. So it's a search for features which are able to represent the variability in the minimal sense, right? So that's a real search for that. There are about half a dozen groups in the world working on this. It's a tough problem because there's something called inversion problem of going from the speech signal to the articulatory mechanism. It's known to be a many-to-one mapping, one-to-many mapping. So there are many optimization algorithms, lot of math based on electrical line analogs and so on, which try to come into the picture to allow you to solve the inversion problem, right? But essentially it's an unsolved problem even now. And one of the tutorials in the InterSpeech conference was only on this, about how to deal with articulatory parameters and how to incorporate it into the speech systems. Still not been done, And it's a very big open area to be done. I'll just play the articulatory picture. It's an MRI scan, X-ray scan. And it's known that when you produce speech, the kind of muscle groups that are acting is about 120 muscle groups. It's the most complex dance, more complex than a sport you could play or a dance you could dance. That's what a child of 2 years old picks up in no time, right? I hope it runs. Let's see. No.
When it comes to singing, I love to sing French art songs. It's probably my favorite type of song to sing. I'm a big fan of Debussy. I also love operas. I love singing Donizetti and Mozart and Strauss. But when I listen to music, I tend to listen to hard rock or classic rock music. And one of my favorite bands is ACDC.
So you got the idea of how the articulators are really dancing around to produce the speech. But still, if you can map the short-term time domain signal to the articulators in some coordinate space. So there are various coordinate systems that can be derived by looking at the cross-section. This is called the mid-sagittal cross-section. And people have come up with people have come up with various coordinate spaces where you can parameterize the articulatory space. And the question is, how do you get there? From the time domain signal, can you get there? This is why I told you the inversion problem. There are enough techniques of it, but none of them very reliable. They're very difficult to, computationally very difficult. Manjunath in his thesis followed a regression problem. It's called a vector-to-vector regression. He used a deep neural network because DNNs can approximate any function. So he said, why don't I train my DNN to take the input signal and map it to these articulatory features. So he created a certain articulatory feature groups called place of articulation, man of articulation, roundness, frontness, height. The idea is, within this lattice, for place itself, I don't have the slide, I think. Yeah, I don't have that. So here, yeah. The place itself has 9 positions, manner itself has 6 positions, roundness has 4 positions, frontness has 5, height has 6. The idea is any input signal which belongs to one of the 50 different sounds in the language has a coordinate here, right? It's a coordinate here. So the idea is to get that coordinate out from the DNN prediction. And he got fantastic results of DNN 5-layer and 1-layer. He got improvements up to 90%. So the articulatory features are being predicted with 90% accuracy. So the question is, you really managed to bring the variability in control by doing this. Then what he did is he put all of them into a fusion, which is called early fusion in statistical pattern recognition. And he did the fusion and obtained consonant-based performance, all articulatory feature-based performance, and vowel-only based performances. And we have some very good results of the predicted articulatory features up to somewhere around 32%. Going by the fact that these are 5-hour data sets, which is peanuts, right? These are all about 3 to 5 hours data sets. That's kind of the state-of-art performance we can get, and that's why it was published in InterSpeech. And important thing is, when we said each of the sound can be decoded in this grid. Hey, where's the grid? Yeah, in this grid. If each of the sound can be decoded as by the oracle says, hey, you know what, a sound is labiodental, it's also fricative, it's also a consonant, and it is closed mid. If it can do that coordinate by oracle, you can reach sub 10%. So this system shows, in principle, if you get the signal to articulator feature mapping correct, to the extent it is close to oracle, you have a sub 10% system for multilingual speech in Indian languages. One of the only result we have so far on this, and hopefully his thesis will uncover more of this. Now he also applied the multilingual phone set. So what did he do? He took all the languages. He said Indian languages have a lot of commonality. They have a large shared phone set. He created a multilingual phone set by mapping every phone into something called the IPA chart. IPA chart is basically International Phonetic Alphabet, which can create a coordinate for a phoneme in any language in the world. Could be Swahili, could be Kalahari Desert, Bushman's language, Click language, or Andaman Nicobar. Everything has been mapped into the IPA alphabet. So he created IPA chart for all the languages in whatever he's considering, 6 languages, and he created the IPA mapping, derived the phone set, and then he used it for an important problem called code mixing. Code mixing is very apparent, like in a multilingual society. Half the things I say in Hindi, then in my mother tongue, then in English, and then how do you make the engine decode it? Currently attracting a lot of attention. So what he said is one of the good old ways will be to run the speech through a language identification system. And the language identification system keeps on saying, now it is English, 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 now it is Hindi, now it is Malayalam, now it is back to English. Then what you do on each short signal, you activate that engine in that language. That's very messy, and he didn't like it. So he went for a multilingual phone engine, which is good for any of the languages. So what you get as output will be a multilingual decoding, which doesn't have to sweat out about finding what language it is, right? And again, you use the same 5-hour corpus, and this part is not so relevant, but this interesting, very crowded, busy graph shows that when the duration of the input increases, 2 things happen, right? One is the LAD accuracy gets better because LAD as a pattern classification problem likes to have more data. So if you speak in Urdu, I may not get it in 50 or 500 milliseconds. If I wait for sufficient long length of time, I know what you're speaking, because there's something called the grammar of the phonemes. It's called phonotactics, which is basically the kind of n-gram structure of the phoneme sequences that plays a role. This is well known from Shannon's time, right? That is the effect you're seeing here. But what happens is, as the LAD accuracy increases, your phoneme error rate starts coming down, which is good because your LAD is making less and less error, and your phoneme error rate comes down. But you need to wait for a full 6 seconds before your phoneme rate is acceptable. But this multilingual system said, hey, no sweat. I don't have to give me any 6-second length of data. Even with 500 milliseconds of data, I can give you what the system will approach asymptotically. Very significant result. He has submitted it to one of the another flagship conferences called ICAS. And he used here a code switch data between Kannada and Urdu, right? He has did enormous amount of work on this. It's very difficult even to work with 5 hours of data. He created the data, manually labeled it, worked with the code mixing data, and you can ask these students how much time he spends between this row and here. He does a lot of things, right? So these are very good results he has got out of his thesis, and let's hope he kind of concludes well. I am at 5 minutes, very good. So one topic I finished in 5 minutes. So next is I'm going to talk about Vikram's co-articulation modeling. So co-articulation modeling is essentially the co-articulation is a very simple phenomenon. When you speak, when you say flu, the last phoneme, which is u, is already influencing the way I speak flu. So by the time I say L, my lips are rounded. The lip rounding is unique to the u sound. So as a kid, in 2 years, I learned a lot of shortcuts. The human species learns to optimize the way we speak. Like you mentioned about energy efficiency, we are very good. We want to spend little effort in talking. So the system knows what I'm going to speak before and after. So at any particular time, if I'm going to say a particular phoneme, I know that I've prepared to say that well in advance. And what I have said now lingers on. It affects what comes later. This is called co-articulation. So if you see the speech in a time axis from left to right, it means the given phoneme is co-articulated with the previous phoneme, previous several phonemes, and co-articulated with the successive several phonemes. And why is this important to model? People knew this from 1991. Kai-Fu Lee, who is now in Google, he's the head of Google Beijing. He had a seminal thesis on saying that your acoustic model, I showed you the acoustic model, the monsters R and the E. He said, hey, don't model the R as a one lot. That R itself comes in many shades. Like you see in color, they come in different hues. It is colored by what is the preceding vowel, what is the preceding phoneme, what is the successive phoneme. So the R space itself is partitioned into several groups. How many groups? If there are 40 phonemes in a language, 40 left, 40 right. So 1,600 shades are there for every phoneme. He said, build acoustic models for every shade. That is going to be more precise than you trying to fit one model for the entire, what is called context-independent vowel or context-independent phoneme. He said, don't use context-independent phoneme, go for context-dependent phonemes. It was a major breakthrough. And nobody looked back after that. So his work was seminal. And after that, people said, even now, today, Google, Cortana, Siri, they will have context-dependent phones. To the extent IBM went on to say, why left context, right context? I'll go to quad context. So they were called quad phones. But not much improvement, but IBM established the trend for quad context, right? Quad context systems. So the co-articulation modeling is very important to tell you, hey, how will I now migrate from a context-independent phone to a context-dependent phone? How will I absorb the co-articulatory process into my modeling to build a statistical model? So here, if you look at this sentence, Joe brought a girl, you can see the phonemes going in a sequence. There's a lot of things happening between any two phonemes. As you see, none of the phonemes have a discrete boundary. The phonemes are all telescoping into each other. That is the co-articulation effect. So it's like somebody remarked, speech is nothing but on a conveyor belt, you put a lot of eggs and smash them. And you can't ask them to be unsmashed. So the machine has to do the unsmashing. And that's where the co-articulation model comes. And this is going to be simply represented as one dimension of the articulator. If this is the target it has to reach, if this is the target it has to reach for one phoneme, next phoneme, next phoneme, we think there is a transition function which governs how it moves from one place to another place. And this transition function could be very long because of the long co-articulation effects. So this function has not been understood at all. People haven't understood, even from the old speech science to even data-driven techniques, there's no clear understanding of how this co-articulation happens. So the interesting thing to go back to ask about this co-articulation is something called the motard theory. The motard theory says, when I'm talking, or rather, let's take a listening. I'm listening, and I'm listening to somebody talking. What I am doing is, I am talking all the time, talking silently, which means motard theory says, when you talk to me, I'm listening, but in such a way, inside, I am calibrating what you're speaking. I'm synthesizing silently what you're speaking, only then I decode what you're speaking. So this is called the motard theory. This holds good for anything else. Even if you watch a tennis match, motard theory goes to the extent of saying, somewhere in your mind, you know how you would be playing the shot. So in fact, I gave a talk in IIC. Silamutala said, now I know why listening to a talk is so tiring. I must be talking all the time inside me. So that's what is happening. The interesting thing about this is the computational aspect is there is a distal event, right? Somebody is talking and somebody is listening, and the proximal stimuli is the signal that you receive. But what is happening inside is you are synthesizing the speech to check whether that's what you have spoken. So what you're doing is you are creating hypotheses about what you might have spoken, and then using the hypothesis, you are synthesizing internally and comparing what you synthesize internally in some abstract representation with what you're really listening, right? So this is really remarkable, and this has been supported by neuroscience called mirror neurons. What did mirror neurons say? It says listening to speech activates motor areas involved in speech production. This is fantastic. It's a major breakthrough in neuroscience, and there are books written about it. So this is from a talk which I gave in Dhirubhai Ambani Institute. And simply put, the computational equivalent of motor theory is to go to something called analysis-based synthesis. It says, I understand what you're saying by synthesizing something and analyzing what you've said with what I synthesized so that I know for sure this is what you would have spoken. It's not very easy to put it in a computational framework, but the ABS does that. Analysis-based synthesis does that. What it does is, basically it says, I have from the input feature space, which is there by listening, the machine has that input feature space, right? Maybe articulated descriptions, maybe from an immersion problem or Manjunath's predicted articulated feature. You will derive hypotheses about what sounds might have been spoken at this point, at this point, at this point. You're not sure, you're creating a lattice because this could be the first best, second best, third best. And in our terminology, we call it as a Viterbi n best path. So we create a Viterbi lattice. And what we want to do is, we want to use this to synthesize various possibilities that might have been spoken and fill in the data, right? So we have high reliability places where recognition is very good, and I want to use a synthesis procedure to be able to generate synthetic data in some abstract space, compare the two, and feed it back to the error in trying to find out what might have been spoken. This is phenomenal. It has been followed by Bell Labs and many other people for quite some time. And this was the thesis of my thesis supervisor, Paliwal and Rao, where they said, do the same thing, but the matching you do in the formant space. Formants are nothing but short-term spectra moving in time. So if I hypothesize that what has been spoken is square, 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 for the square I have a spectral envelope here, for the circle I have the spectral envelope here, I interpolate between them and check which of these combinations give me the interpolation that best matches with what is actually observed. This is a very old formulation, but this is still very active in asking, I'll skip this, in asking the question, for instance for Vikram, would be to ask, can I create the synthesis function here by using something called temporal decomposition, right? This is again a work by Bell Lab, by Vishnu et al, who was decorated with the ISCA medal in the Interspeech Conference. It says, I can look at speech as being able to reach certain articulatory positions described by those transfer functions, but I have articulations which are overlapping in time, which are the co-articulation functions. He had a math based on singular value decomposition to solve for both. Solve for both, which means you are given input speech, you can find the target positions and what is called as the co-articulation functions. Now what does it do? It gives you a handle to go back to this space and say, okay, I can do this in articulatory space, I can do this in articulatory space, I can create the synthesis from a temporal decomposition. This is just active, I mean, wide open to be done. And these are the kind of thoughts that probably will go into creating a computational analog of the mota theory. Could be analyzed by synthesis, maybe using temporal decomposition or by some other co-articulation modeling. So what we have done typically is to model the co-articulation. So what you have done is to ask, how will these two units get co-articulated to fill in, right? So that is essentially one of the directions we are looking at. I'm at 3:15, good. I'll go to the next topic. This is the topic by Chella and Anup for the MTech project, which was again published in Interspeech. They are basically semi-supervised and active learning scenarios. We called it as efficient acoustic model refinement. So some of you are asking question about whether the adaptation is at the what level, right? It could be at the acoustic model level, which is the predominant effect. And here we are talking about almost like we use in other machine learning terminology called never-ending learning. Data keeps coming in and system is able to make decisions on the data, and if the decisions are reliable, so you should know when they are reliable because nobody is going to tell you. There's no person sitting there as an oracle and says, now you got it right. So you need to make the decision. If you got it right, you reuse the data to make your Amazon Alexa do better over time, right? So that's the work they did, very contemporary and topical. And I'll skip this, and I'll just read something from Google's 2014 paper where they hit upon exactly this problem as something plaguing them. So what they said is in this paper, see, this is big data approach to acoustic model training, corpus selection, which is equivalent to saying, I have a legacy data. This paper is about 30 years of data, which Google has got from their Google Voice Search, which wasn't working at the time before, but they have the data logged in. 30 hours of data, 30 years of data is roughly, I don't remember, 20,000 hours of data. So what they said is, we describe Google's approach to constructing speech corpora and models in a fully unsupervised manner, which means there's no oracle telling you when the engine has got it right. That's why it's called unsupervised. Our process is based on redecoding a massive amount of anonymized audio logs from Google's speech product using a high accuracy non-real-time system followed by a series of heuristics aiming at discarding incorrectly recognized speech, or the way we are doing it, to select correctly recognized speech according to some proxy metrics. Such an automated procedure enables the collection of training sets an order of magnitude larger than what we can typically obtain by human transcription. We don't need humans to transcribe it. Moreover, our use of a large-scale distributed computation platform and so on. That's not important. But the point is, we are looking at this problem of asking whether Amazon Alexa or Google Voice Search can reuse the data that it keeps getting. So you use the Google Voice Search. You said, show me the map of Electronic City. It decoded it something else. It gave back a result to you. Maybe you are happy with it or you're not happy with it. I have no means of knowing it. Of course, I can ask for a thumbs up, thumbs down. It's all laborious. We don't want to do all that. But internally, as a decoding process, can I have a reliable proxy of when the system is correct, which parts of the speech it is correct, and reuse it for adapting my acoustic model, so that over time, my acoustic model is exposed to more new data, it starts doing better without me asking for data from anywhere. I don't have to pay for the data, I don't have to label the data. I can it's just crowdsourcing coming free, right? So that's the work we did. We had two scenarios. One is we have a small seed corpus. It's like Google Voice Search goes to shipping with acoustic model, which is not good. It never happens, it's very good. And it's a small seed corpus, and that is a small acoustic model. Then you have a huge corpus, which is, let's say, coming in from the device on a daily basis, but you have to decode it and the decoding is erroneous, and you have to ask how will I select data from the erroneous decoded data to retrain my acoustic model. Or the active learning scenario, what happens is I have a small D seed, a lousy acoustic model, and I have a large data which is unlabeled, right? I decode this using the small seed data. I get a lot of decoding, but from here I want to ask a different question. Not the data which is more accurate, but the data which is least accurate. Why? Because it is that data which is useful for me to label manually, which means I'm going to hire some people to label manually, but I want to minimize that effort. So I'm asking the question, instead of 1,000 hours of data being manually labeled, can you give me the 100 most useful data, which is most informative, to make my seed model better? Which means it has to see data which is complementary to what it has seen before. So therefore, you're going to look at data which is more erroneously decoded to be manually labeled, and then to improve the acoustic model. This is essentially the work they did. I won't spend too much time on this. A lot of math details on this in terms of what kind of measure you use to detect when the data is more accurate or when the data is not accurate. And we had iterative algorithms, 3 kinds of iterative algorithms, and basically we showed one result, which is this result, which said if I were to increase the way I use the decoded data, large amount of data, in our case it was 5 hours of data, which by itself is not much. The seed data was itself built on 1 hour. The amount of data we have to reuse is about 3-4 hours, and the test data was about half an hour. Imagine this being scaled to Google's 10,000 hours of data. The principle works, but we need to get there, right? The principle says, if this is the ground truth I can reach, if all the data were manually labeled correctly, and if this is what I start with the lousy acoustic seed model, I can reach halfway by using this at no cost, free for use kind of algorithm, which uses the semi-supervised learning, right? So I'll stop this. Active learning is a little more involved. I'll skip this part, and I just want to spend the last 10 minutes on Srikanta's work, which are called end-to-end approaches on attention-based model. Very contemporary. Papers are being published only since last year, and it's a very tough area, mainly because they look fancy because they start from signal and go to the words or letters by dissolving the architecture. The architecture has gone. The original block diagram I showed you is not there. How do you do it, right? They managed to do that, right? And within this, the last 1 year trend is to put in something called attention, which says the end-to-end system pays attention to some parts of the data to come up with the right classification, to right labeling, right? So essentially what we are saying is the block diagram goes, and you essentially have a signal to symbol, like it says cat. What has been spoken is cat, by using a fully neural architecture. And of course, this can come in many shades. You could have representation layers, like I told you, which extract features, and there could be feature transformations, which are happening via DNNs, or you could have RNNs and LSTMs, which deal with this as a sequence of features and try to convert this feature sequence to a letter sequence. Those are all done by RNN, LSTM kind of architectures. Anything could be happening here. They all come under end-to-end models, right? And typically, the system will give an error output like this. If what has been spoken is friends, it gives an activation, which is all the letters, all the phonemes. Phonemes are letters directly. It tells you at this particular point of time, those are the letters, those are the phonemes that are most active. You read it out, right? The problem is you need large amount of data. You need large computation time to handle the variability that comes from the signal, because the structure was put in for a certain reason to manage the kind of variability that the system sees. The moment you remove all the structure, the lexicon, the acoustic model, the decoding, search hypothesis, then the system is facing the signal in all its variability, and you have to map all of that variability to the symbol sequence. That's why these are very consuming, time consuming, and data intensive. So a few flavors of this, which leads me to Srikanta's work, is basically systems which can do one-to-one. That is, I have a sequence. I want to map the sequence to another sequence, like what I told you here. Sorry, I'm going the other way. Yeah, here. So you want to generate a sequence, which is probably the sample level sequence, right, to a symbol level sequence. And typically you will do a recurrent neural network, which is the workhorse on which a lot of variants are built in. And there are many kinds of flavors to this. Could be a one-to-one system like a DNN, or one-to-many like image captioning, an image with somebody says a giraffe is standing near the lake, or many-to-one where you have data a text of a review of a movie and you want to say up or down sentiments, or many-to-many like in a machine translation, or in speech recognition where you want to go from signal sequence to feature sequence to letter sequence or word sequence, and many-to-many in video classification like what Dinesh does, right? So this is just a same thing. So the inside, what happens under the hood is essentially called the encoder-decoder mechanism, where your input sequence is mapped by a recurrent neural network. I'm sorry, I'm not able to spend much time on recurrent neural network. It's essentially a sequential conditioning learner, and it finds out an intermediate representation based on all your past inputs. And this particular intermediate representation is mapped back to a target sequence label. This is how a typical many-to-many works, and you can make it one-to-many, many-to-one, many-to-many in the way you want it. And you set up a loss function between what has come out and what you wanted, right? Well, that is the loss function on the output target space. And the interesting thing is, last year people came up with the interesting observation that a machine translation system based on this doesn't work for sentences which are long. Beyond 5-6 words, this starts failing because the entire onus is on this intermediate representation. This kind of system, the encoder-decoder framework, depends on all of this partial input sequence to be mapped to this and to recover the output sequence from here. Then they said, hey, this is very silly because you're putting all the onus on a single representation, spread the mapping to all the intermediate representations, which is RNN's output, the encoder RNN's output. How did they do that? By creating this kind of context window, which means each of the H1, HT is combined in any number of ways. Simplest way will be a dot product with a certain weight vector. There are many other ways. So all the variants of attention-based model comes there. This is the key. This is the key step. And what you do is the RNN's output, you make it conditioned like usual, but also on this so-called attention model. So the attention model, by virtue of what kinds of weight it can choose to give importance to any of the history that comes from the encoder. So in machine translation, where is this useful? Two ways. One is the word ordering can change by just changing the alphas. So you can go for any word ordering to any word ordering much more comfortably than if you do not have the attention. Second thing is there are certain keywords probably which have to be mapped to the output target sequence so that the sentence is considered as translated. So that kind of attention comes into picture here. And so this has been very major breakthrough, a simple mechanism just to describe what is happening. The encoder creates all the H1s, and there is a sliding attention window, which finally leads to the decoder RNN. I won't go into this detail. This is a specific architecture which does it, how the output looks like, and how the performance is now competitive to various other variants. This seems to be the way to go, mainly for the simplicity and its elegance. But the important point is, if you look at the image captioning and ask how did the attention look like, the system, suppose it gives a captioning saying, a woman is throwing a frisbee in a park, you can go and dip into the attention mechanism and realize that the system is paying attention to the frisbee there, right? Likewise, this is remarkable. Dinesh knows about it. Maybe his students are using it. This has not been reproduced for speech. So one of the things we are setting out to do will be to ask, in speech, does it look like it allows the system to focus on certain specific time frequency spaces in mapping the input signal to the phoneme sequence or letter sequence or word sequence. We're asking, are there specific time frequency patterns which the system can pay attention to? This is known by acoustic phoneticians. So there was a professor in MIT called Victor Zhu who can read spectrograms. You'll give this to him, he'll take half a minute and tell you what the speech is. Which means somewhere inside he knows how the time frequency pattern maps to the sequences. This is 30 years back. And all the speech knowledge guys used to say, hey, there's a guy who is a living proof that you need that acoustic phonetic knowledge to make your system work. Nobody lives that. Now I think we are in a position to bring that back within the attention-based model and ask whether the attention does really come into picture, right? So a few other variants is basically, if I can close in 2 minutes, yeah. There are other variants, which is about 2018 paper, which said, hey, why should the output be a letter sequence or a word sequence? Can't I combine both of them? Basically, you have attention at the letter level and the word level, right? And you want to combine them so that you are not plagued with the typical English problem of the, what is called, the English language is notorious for its alignment between the letter and the sounds. If I say phone, it's P-H-O-N-E, but it is F-O-N. So this kind of issues makes it a very tough language, unlike Kannada, which is one-to-one. You speak the way you hear and you write the way you listen, right? These kind of things. So they said, why don't you have a output unit? This is called multi-head attention model, which tries to combine two units of different granularity. In abstract form, that's what it means. You are trying to create architecture, which is a multi-head architecture, which is trying to combine outputs at units which are at different time resolution. So one of the things we want to do is to give the same multi-head architecture to the input, so that we can say, hey, the system listens to speech at multiple time resolutions or multiple spectral resolutions. So how do you create that kind of architecture? So that's one of the things that actually leads us to this notion of acoustic subordinates and zero speech, but I'll stop here. Sorry to Srinivasa Raghavan, whose topic is this, but I'll stop here. Thank you. Yes. Probably the students will have something in the next few months, then we can present that also. I'll ask them to actually talk about that then. Yeah, sorry. Right. Yes. Right. Right. So I would say there are still groups continuing to do that, and about 10 years back, if you ask the question, the kind of groups which are migrated to the data-driven bandwagon, it was less because these are not successful at that time. So there were still speech science people who are either oriented from the biological realism. So when I talk about biologicalism, two things I have to mention. One is from perception point of view, we are talking about what happens till the auditory nerve, which is understood fairly well. So the von Beckersey was the Nobel laureate, got his Nobel Prize for this particular work, to go and dissect the cochlea, find out the mechanism of the basilar membrane. This happened 60, 70 years back, and there's been Nobel Prize, no other Nobel Prize in speech. So it stopped with that. So the mechanism of the biological part of the basilar membrane and what happens to the auditory nerve is understood, but this is about a small minuscule of what happens from the auditory nerve to the real cognition, which is not understood because like in a cat or a dog experiment for a vision, you can't cut open, put electrode, give a stimulus and find out which circuit is doing what. Because speech and language is unique to human. At best, you can do it for auditory sounds in a mammal or a cat, but when it comes to speech and language, you don't know the pathway. So people in Niemann's, for instance, there are groups which work with what are called aphasics. Aphasics are people who have lesions in the brain, which makes them do something wrong with the speech and language. So they try to reconstruct the path of a working brain, knowing what doesn't work. Very tough work, but there are people who are doing this mapping. Now, this also comes under an area called psycholinguistics. And there are very few takers in the last 30, 40 years of engineering research students who try to take a cue from the psycholinguistics to create algorithms which are close to that, very unfortunately. But there are people who are sensitive to the fact that this is not happening, but that's where it is. So it's a gold mine to tap into. The whole business of psycholinguistics, which looks at the pathway, the auditory pathway, and in terms of production mechanism, fairly well is understood. Except the fact that the articulated data is difficult to come by because you need an MRI scan to get a ground truth data of what has been spoken. That is where the immersion problem becomes important, still unsolved problem. The math is very formidable because we still don't know how the articulators map to the sound signal. That's where it is. Right. The Sandhi and right.
Do you think is there any work or attempts to utilize the work in NLP, NLU?
Right. Go back to ASR.
Kind of a hybrid?
Very much. In fact, the very thing you talk about decoding, which is the search of the hypothesis space, where you want to find out what is the best word sequence. I told you about the n-best lattice kind of thing, which means the system is not confident about the top hypothesis. It wants to create a multi-hypothesis system. The algorithms are well known. It comes from computer science, the best path kind of algorithms, A-star kind of algorithms. To be able to rescore this lattice, to say I want to bring in some other knowledge. That knowledge could be a syntax, could be a grammar, could be the semantics. Suppose I'm maintaining a dialogue with you. I expect your answer to be of a certain kind. I can impose it to rescore. It's happening, but that's not the real main stuff that's going on. The decoding guys are interested in that. The dialogue system people are interested in that, but that's not taking on in a big way. It's not the bulk of the work that's happening. Yeah, sorry. Right.
We also probably listen to things because we see things.
True.
We mix visuals with
True.
Are there models
So, true. So these are multimodal perception systems, like Professor Dinesh works a lot on these things. So you take visual cues and try to create associative mappings, or what are called associative labels to what you have listened to. So the same signal can have a multimodal labeling, and you want to derive semantics out of it. It's not a very major thing. Maybe there are half a dozen groups working on around the world on doing such things. Mainly because the kind of data to get is very difficult, to label it is difficult, and to create the associative model is very difficult. So one of the talk I'm giving in the next, one of the next sections is on the associative memory formulation, where we want to look at such multimodal data. But that's probably the way the child learns. So it has all kinds of cues. It doesn't have, so in fact, one of the interesting remark most speech researchers make is, they say Google, the kind of data you use, 50,000 hours of data, if a child were to be exposed to that, it has to be already 1,000 years old to be able to listen to 10,000 hours of data. So it makes do with much little data. That's the graph I showed you. After 2018, we want to go in a direction where the data dependence is less, but the understanding is more, right? Or the performance is more. So it's not clear how child managed to do with so little data. What kind of, it's called immersive experience. I mean, it's immersed in a world and it picks up the language.